Hello, cosmic explorers, and welcome back to Ascended Beyond. For generations we've looked up at the night sky and wondered. We built bigger and better telescopes, each one peeling back another layer of the cosmic onion. Now, we have the James Webb Space Telescope, humanity's most powerful, most ambitious eye in the sky. It's not just another telescope, it's a time machine, peering back over 13.5 billion years to witness the universe's dawn. It's designed to see the unseen, to capture the faint ancient light from the very first stars and galaxies. And what it's finding? Well, it's rewriting the textbooks. The images are breathtaking, of course, celestial ballets of gas and dust, glittering stellar nurseries, and deep fields teeming with galaxies. But beyond the sheer beauty, Webb is delivering data that is profoundly perplexing. We're talking about discoveries so strange, so unexpected, that they leave astrophysicists, the people who are supposed to have the answers, scratching their heads, rerunning their models, and questioning what we thought we knew for certain about the universe's history and its structure. So, buckle up. Because today, we're embarking on a journey to the bleeding edge of cosmic discovery. We're going to explore 10 of the most mind-bending findings from the JWST that currently have scientists baffled. Number 10. The universe's overachievers? Let's start with a big one, literally. According to our best cosmological models, the Lambda CDM model, the universe began with the Big Bang and then slowly, methodically, built itself up. Small structures, tiny fluctuations in density, gradually pulled in more matter through gravity. Over hundreds of millions of years, these small clumps merged and grew into the first small, dwarf galaxies. Only much later would these merge to form the massive spiral and elliptical galaxies we see in the universe today, like our own Milky Way. It's a bottom-up process, a story of slow, patient construction. But when the James Webb Space Telescope looked back into the cosmic dawn, about 300 to 500 million years after the Big Bang, it found something that shouldn't be there. It found galaxies that were, well, huge. These weren't the small, primitive galactic seeds we expected. They were surprisingly massive, shockingly mature, and already brimming with stars. It's like looking at a photograph of a 2-year-old toddler who happens to be 6 feet tall with a full beard. It just doesn't fit the timeline of cosmic development we've so carefully constructed over decades of observation and theory. This discovery throws a cosmic wrench into the works, proving out current laws of physics might be incomplete. How could these galaxies have accumulated so much mass, so much gas, and converted it into stars so quickly? It's as if they skipped their cosmic childhood and adolescence entirely and jumped straight to adulthood. The data suggests that either the process of galaxy formation is far more efficient and rapid than our models predict, or the very seeds of these galaxies, the dark matter halos they form within, were much larger, much earlier than we thought possible. Scientists are now scrambling to figure this out. Are our models of early star formation wrong? Is there some unknown mechanism accelerating galaxy growth? Or could it be that our understanding of dark matter, the invisible scaffolding of the cosmos, is incomplete? These impossible early galaxies aren't just a curiosity, they represent a fundamental challenge to our entire story of cosmic evolution. Webb has shown us the first chapter of the universe's story, and it seems we've been reading the wrong book. Number 9. Cosmic oddballs. When you think of a galaxy, you probably picture one of two things: a majestic swirling spiral like our Milky Way, or a big roundish blob of stars known as an elliptical galaxy. For decades, the Hubble Space Telescope reinforced this view, showing us a cosmic zoo dominated by these familiar shapes, with a few irregular ones thrown in. We developed classification systems, like the Hubble sequence, to neatly categorize what we saw. We thought we had a pretty good handle on galactic morphology, the study of their shapes and structures. Then Webb turned its golden eye to the distant universe and found, well, cosmic weirdos. It began spotting galaxies with shapes that defy our neat little boxes. We're not just talking about slightly irregular galaxies. We're talking about long, thin, chain-like galaxies that look like cosmic necklaces. We're seeing galaxies that are incredibly flat, like cosmic pancakes dubbed disk galaxies, which are far more common in the early universe than previously thought. And then there are the green pea galaxies, compact, round, and intensely green due to extreme bursts of star formation. These shapes are deeply problematic for our theories of galaxy formation. A long, thin chain of stars is a very unstable configuration. gravity should quickly pull it into a more compact, spherical or disc-like shape. How did it form, and how has it survived? The abundance of pure disk galaxies without the central bulge of older stars we see in modern spirals suggests a different, more chaotic formation path, perhaps from vast, rotating filaments of gas collapsing directly into a disk, bypassing the messy merger phase we thought was essential. This menagerie of bizarre forms forces us to rethink the environmental and physical processes that sculpt galaxies. Were the dynamics of gas and dark matter in the early universe fundamentally different? Was galactic evolution less about orderly mergers, and more about a wild, experimental phase of cosmic creation? Webb is showing us that the universe wasn't just building galaxies in its youth, it was doodling, experimenting with forms and structures that are rare or non-existent today. It's a beautiful, chaotic, and utterly baffling glimpse into the universe's creative process. Number 8. Beacons in the primordial fog. Imagine peering back into the very early universe, a time known as the cosmic dawn. The first stars are just beginning to switch on, burning away the neutral hydrogen fog that filled the cosmos since the Big Bang. In this primordial darkness, we expect to see faint glimmers of light. What we don't expect to see are cosmic lighthouses blasting at full power. Yet that's precisely what the James Webb Telescope has found, super bright quasars shining with the light of a trillion suns, much earlier in cosmic history than we thought possible. A quasar, for those who don't know, is not a star. It's the intensely luminous core of a distant galaxy, powered by a supermassive black hole actively feeding on surrounding gas and dust. As material spirals into the black hole, it heats up to incredible temperatures and radiates an immense amount of energy across the electromagnetic spectrum, outshining the entire host galaxy. To have a quasar, you first need a supermassive black hole, one with the mass of billions of our suns, and that's the problem. According to our standard models, black holes start small from the collapse of a massive star and grow over time by merging with other black holes and accreting matter. It's a process that should take billions of years. Finding a fully formed, supermassive black hole powering a brilliant quasar less than 1 billion years after the Big Bang is like finding a fully grown redwood tree just 1 year after planting a seed. The timeline doesn't add up. There simply hasn't been enough cosmic time for it to grow that big through the conventional channels. This discovery has theorists searching for answers, like it's a cosmic Easter hunt. How do you grow a black hole that fast? One idea is the concept of direct collapse black holes, where a truly enormous cloud of primordial gas collapses directly into a massive black hole, skipping the star phase entirely. Another possibility is that the early universe was much denser, allowing for hyper-efficient feeding. Webb's discovery of these ancient, overly bright beacons isn't just a puzzle, it's a direct challenge to our understanding of the formation of the universe's largest and most enigmatic objects. Number 7. Alien atmospheres and chemical ghost. One of Webb's most exciting capabilities is its power to analyze the atmospheres of exoplanets, planets orbiting other stars. It does this using a technique called transit spectroscopy. When a planet passes in front of its star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere. By analyzing the spectrum of that light, the specific colors that are absorbed, we can deduce the chemical composition of that alien air. It's an almost magical way to perform chemistry on a world light years away. We expected to find the usual suspects: water vapor, carbon dioxide, methane, the building blocks of atmospheres as we know them, and Webb has found those. But it's also finding things that are odd. For example, on WASP-39b, a hot gas giant located 700 light-years from Earth, Webb detected a surprisingly strong signal for sulfur dioxide. This was a genuine shock. On Earth, sulfur dioxide is primarily produced by photochemical reactions, sunlight breaking apart other molecules. Its presence on WASP-39b suggests similar chemical processes are happening on a world vastly different from our own, but it gets weirder. On other exoplanets, scientists are finding a distinct lack of certain molecules they fully expected to see. For instance, on some hot Jupiters, methane should be abundant at the temperatures and pressures involved, yet Webb's instruments have found little to no trace of it. Where did it go? Is it being broken down by some unknown chemical process? Is it being obscured by exotic clouds made of materials like silicate, essentially tiny grains of sand or glass floating in the atmosphere? These atmospheric anomalies are forcing us to rethink our models of planetary chemistry. The universe, it seems, has a much more diverse chemical cookbook than we imagined. Each new spectrum Webb delivers is a new recipe, with missing ingredients and surprise additions. We're not just looking for signs of life, we're first trying to understand the fundamental rules of chemistry on worlds completely alien to us. And those rules are proving to be stranger and more complex than we ever anticipated. Number 6. Water here, water there, water everywhere. The mantra for the search for life has long been follow the water. On Earth, wherever we find liquid water, we find life. So, finding water elsewhere in the cosmos is a top priority. We found it locked up as ice on Mars and in the moons of Jupiter and Saturn. Webb, with its powerful infrared vision, is uniquely suited to detect the signature of water vapor, the gaseous form of H2O, and it's finding it, but in some very strange locations where it has no right to be. One of the most surprising discoveries came from the protoplanetary disk approximately 370 light-years away from Earth around a young star called PDS-70. This is a system in the process of forming planets. Webb detected a large quantity of water vapor right in the inner region of the disk, the very place where terrestrial rocky planets like Earth are thought to form. This is puzzling because the intense radiation from the young star should, in theory, break apart water molecules, a process called photodissociation. The water should be gone, or at least confined to the icy outer regions of the disk. So why is it there? How did it survive? One theory is that the water is being shielded by vast amounts of dust in the disk, which absorb the harmful radiation. Another more exciting possibility is that the water isn't primordial, it's being delivered continuously from the outer, icier parts of the system. Tiny icy dust particles and even larger comets could be migrating inward, releasing their water vapor as they get closer to the star. This would mean that the building blocks for life-sustaining oceans are available right where rocky planets are born. This isn't the only odd discovery. About 26 light-years away from us, Webb has also found water vapor in the atmosphere of a super-Earth exoplanet, GJ486b, orbiting extremely close to its red dwarf star, Gliese 486. The planet is a scorching 800 degrees Fahrenheit, or 426 degrees Celsius, and it was thought to be too hot and too irradiated to retain any atmosphere at all, let alone one with water. Scientists are now debating if the signal is truly from a planetary atmosphere, or perhaps from cool star spots on the host star itself. Either way, Webb is showing us that water is more resilient and more widespread than we thought, popping up in the most unexpected and hostile cosmic environments. Number 5. A deeper darkness. Let's talk about something we can't see, but we know is there, dark matter. It's the mysterious, invisible substance that makes up about 85% of all matter in the universe. We can't detect it directly, but we see its effects everywhere. Its gravity is what holds galaxies together and what bends the path of light from distant objects in a phenomenon called gravitational lensing. Our standard model of cosmology, lambda CDM, assumes dark matter is cold, meaning it moves slowly and clumps together easily, forming the gravitational scaffolding for galaxies. For the most part, this model has worked beautifully, but the James Webb Space Telescope, with its unparalleled sensitivity, is starting to see subtle inconsistencies, anomalies in the way dark matter seems to behave. By studying the distorted shapes of the most distant galaxies, Webb can create incredibly detailed maps of the dark matter that's doing the distorting. And in some of these maps, things don't quite add up. The distribution of dark matter doesn't perfectly match what our cold dark matter simulations predict. For example, in some galaxy clusters, the core seems to be less dense with dark matter than expected. In others, the distribution seems smoother or more diffuse. These aren't huge, glaring errors, but they are persistent, subtle deviations from the model. It's like listening to a beautiful symphony where a few instruments are consistently ever so slightly out of tune. You might not notice at first, but the more you listen, the more it bothers you. These anomalies have opened the door to more exotic theories about the nature of dark matter. What if it's not entirely cold? What if some of it is warm, or fuzzy, with properties that cause it to resist clumping on smaller scales? Could dark matter have some form of self-interaction, a kind of pressure that pushes it apart in the dense cores of galaxy clusters? Webb can't tell us what dark matter is, but by precisely measuring what it does, it's providing crucial clues. It's hinting that this invisible cosmic glue might have a richer, more complex nature than we ever imagined. Number 4. The cosmic web's threads. On the largest scales, the universe isn't a random spray of galaxies. It has a structure, a magnificent, intricate pattern known as the cosmic web. Galaxies are arranged in long, delicate chains and vast, flattened sheets, all interconnected. These are the cosmic filaments, unimaginably huge structures of gas, dark matter, and galaxies, stretching for millions of light-years. They are the superhighways of the cosmos, funneling matter into the dense intersections where galaxy clusters form. We've known about this web for a while, but seeing it directly has been a challenge. The James Webb Telescope, however, is starting to trace these filaments with unprecedented clarity, especially in the early universe. It recently imaged a protocluster, a galaxy cluster in the making, and found it being fed by a colossal filament of gas stretching over 3 million light-years. This structure contained a mass equivalent to 1 trillion suns and was home to 10 burgeoning galaxies. Seeing this structure so early in cosmic history was a triumph, confirming our models of large-scale structure formation. But Webb is also finding things that don't fit. It's detecting filaments that are much more tenuous and defined than expected. More perplexingly, it's finding galaxies that seem to exist in vast cosmic voids, far from any obvious filament. How did they get there? Did they form in isolation, which would challenge our understanding of galaxy formation? Or were they somehow ejected from a nearby filament with incredible force? It's a cosmic conundrum. Furthermore, some of the light from the earliest quasars, which passes through this cosmic web on its way to us, shows absorption patterns that are difficult to explain. The gas in the web seems to be clumpier and more turbulent than our simulations suggest. It's as if the cosmic web has a more complex and dynamic weather system than we accounted for. These mysterious cosmic filaments, and the voids between them, are no longer just theoretical concepts. They are real places that Webb is exploring, and they are proving to be full of structural surprises. Number 3. Whispers in the infrared. The James Webb Space Telescope is an infrared telescope. This means it sees light that is invisible to the human eye, light with longer wavelengths than red light. This is crucial for 2 reasons. First, the light from the most distant objects has been stretched to infrared wavelengths by the expansion of the universe, a phenomenon called redshift. Second, infrared light can pierce through the dense clouds of cosmic gas and dust that obscure our view of things like stellar nurseries. Webb was built to see the universe in the infrared, and it's doing so with spectacular success. But in its deep, long-exposure images, it's picking up whispers, faint signals, unexplained sources of infrared light that don't seem to match anything we know. In images of seemingly empty patches of sky, after all the known stars, galaxies, and quasars are identified and subtracted, there remains a faint, diffuse glow. This is known as the cosmic infrared background, and part of it is expected. It's the combined light of all the stars and galaxies too faint to be seen individually. But the glow Webb is detecting seems to have strange fluctuations and patterns within it. There's an excess of light at certain infrared wavelengths that cannot be explained by our current models of star and galaxy populations. So, what is producing this extra light? This is one of the most profound mysteries to emerge from Webb's data so far. It's a signal from the cosmos, and we don't know who or what is sending it. The theories are flying. Could it be the light from the very first generation of stars, the so-called population 3 stars, which were thought to be enormous and short-lived? Could it be the faint heat from primordial black holes accreting gas in the dark ages of the universe? Or could it be something truly exotic, like the decay of some unknown type of particle from the dark sector of the universe? Right now, we simply don't have an answer. Webb has heard a strange whisper from the cosmic dark, and we're all leaning in, trying to make out the words. Number 2. Methuselah's children. Here's a discovery that sounds like it should be impossible. A paradox that cuts to the very heart of our understanding of time and the cosmos. The universe, according to our best measurements from the cosmic microwave background and the rate of cosmic expansion, is about 13.8 billion years old. This is the ultimate speed limit, the age of everything. Nothing can be older than the universe itself. It's a fundamental tenet of modern cosmology. The James Webb Space Telescope, by looking at some of the oldest galaxies, is allowing us to study their stellar populations in great detail. By analyzing the light from these ancient galaxies, astronomers can estimate the ages of the stars within them. This is done by looking at their color and brightness, which tells us where they are in their stellar life cycle. Redder, dimmer stars are typically older. And in a few of these extremely distant early galaxies, Webb has found stars that appear to be well, older than the universe. Now, let's be very clear. No astronomer seriously believes these stars are actually older than the universe. That would break physics as we know it. But the data, when interpreted through our current models of stellar evolution, points to this impossible conclusion. It's a situation where our observations are in direct conflict with our theories. It's what we call a cosmic paradox, and it means something somewhere in our understanding is fundamentally wrong. So what could be the explanation? One possibility is that our models of stellar evolution for the very first stars are incomplete. These stars were made of almost pure hydrogen and helium, the pristine material from the Big Bang. Perhaps these metal-poor stars evolved differently, burning their fuel in a way that makes them look older than they really are. Another more radical idea is that our measurement of the age of the universe itself might need a slight revision. Or perhaps the light from these stars has been altered on its long journey to us in ways we don't yet understand. Whatever the answer, this Methuselah star problem is a baffling and profound puzzle. Number 1. Black holes on a binge. We've already talked about the problem of supermassive black holes in the early universe, but the issue of their growth isn't just confined to the cosmic dawn. Webb is looking at black holes across cosmic time, and it's finding that many of them seem to be growing much faster than our theories allow. There's a theoretical speed limit to how fast a black hole can grow, known as the Eddington limit. Think of it like this. As a black hole pulls in gas and dust, that material heats up and shines brightly. This outward radiation pressure acts like a wind, pushing back against the infalling material. If a black hole tries to feed too quickly, the radiation it generates becomes so intense that it literally blows its food away, choking off its own growth. The Eddington limit is the point of equilibrium, the maximum rate at which a black hole can accrete matter without shutting down its own buffet. But Webb is finding black holes that appear to be consistently super Eddington, meaning they are accreting matter far above this theoretical limit. It's not just by a little bit either. Some appear to be growing 5, 10, or even more times faster than what we thought was the physical maximum. We can tell this by measuring the brightness of their quasar, or active galactic nucleus, and comparing it to the estimated mass of the black hole. The numbers just don't line up with the theory. How is this possible? Scientists are exploring several ideas. Perhaps the gas flowing into these black holes isn't uniform. If it's clumpy and porous, the radiation might be able to escape through channels without blowing all the gas away, allowing for a higher overall accretion rate. Another idea is that these black holes are growing through a different mechanism, like rapid successive mergers with other black holes or dense star clusters. Webb's observations are forcing a major rethink of the physics of black hole accretion, suggesting these cosmic monsters have secret, more efficient ways of feeding their insatiable appetites. So there you have it. From impossible galaxies and supercharged black holes to alien atmospheres and whispers from the cosmic dark, the James Webb Space Telescope is not just answering old questions, it's posing a whole new set of questions. We sent it up to confirm our picture of the cosmos, but instead, it seems to be showing us just how much we still have to learn. Each of these discoveries is a breadcrumb leading us down a new path of inquiry, a new avenue of exploration that could lead to a revolution in our understanding. This is what science is all about. It's not about having all the answers. It's about the thrill of the chase, the joy of the puzzle, and the humility to admit when the universe is stranger than your theories. The data from Webb is just beginning to pour in. We are in the first few minutes of a feature-length film about the cosmos, and it's already filled with plot twists. The coming years will see scientists around the world grappling with these baffling findings, building new models, and designing new observations to test them. So, I would love to hear from you. Which of these discoveries blew your mind the most? Was it the stars that seem older than the universe? The water popping up in impossible places? Or the mysterious infrared glow with no known source? Let me know in the comments. Leave a like so I know you enjoyed the content, and remember to keep looking up, keep asking questions, because as Webb is so beautifully demonstrating, the universe is not only stranger than we imagine, it may be stranger than we can imagine. Thanks for watching.